It's gonna be a thin population kind of a day, huh? Okay. So I had a couple more to go over on the exam. I didn't get through the last two, and so I'm going to ask about yours. All right. So you had to determine the interval of convergence of this. You had 2x minus 7 to the k over k to the 5/2. Okay, so you set up ratio test. That's typically the way you you do these. I think you probably could have done this by root test, but ratio test is okay. I think it's easier. So AK is 2x minus 7 to the k over k to the 5/2. AK plus 1 looks very similar. Alright, so in particular, if I look at the limit as k goes to infinity of AK plus 1 over AK in absolute value, that is the limit of what? 2x minus 7 to the k plus 1 over 2x minus 7 to the k. And then I've got k plus 1 to the, I guess that's going to be on the bottom, doesn't matter, but k plus 1 to the 5/2, and then k to the 5/2 on top. And of course this limit of ratios of k's, that just goes to 1. And so this is just absolute value of 2x minus 7. So if I set that less than 1, that means 2x minus 7 is between 1 and negative 1. And so that means 2x is between 8 and 6, is that right? Yes. Yep, so x is between 3 and 4. So that's about half of the question. If you stopped here, you got points off because you didn't check the endpoints. So at x equals 4, the sum of 8 minus 7 to the k over k to the 5/2, which is just 1 over k to the 5/2, that converges because it's a p-series, p greater than 1, right? Okay, and at x equal to 3, the series 6 minus 7 to the k over k to the 5/2, which is negative 1 to the k over k to the 5/2. Well, it converges absolutely because that converges. So in particular it converges. Okay, so, and I believe you did have to say that it converged absolutely. A lot of people told me that was an alternating harmonic series. That's not a harmonic series, that's a p-series. Harmonic series is specifically p equal 1. So what that means is your interval of convergence is this. So your interval of convergence is 3 to 4 brackets on both ends. Alright. Lastly, the Taylor series problem. finding the Taylor series problem anyway. I wanted a marker that writes well, and I should have been more specific.
Terrible marker.
Really is. We're terrible at racing.
You wanna try a different marker?
Yeah.
I got two.
Really?
You want a purple one or a brown one?
Purple, of course.
Heck yeah.
Alright, give her a shot. Alright, it writes, and it smears. We'll see. Yeah, we may end up with sort of a psychedelic wash on the blackboard at the end here. So I've seen that happen before. It's a lot of different colors. So if you got f of x was 2x minus 7 to the negative 1. So what you're going to have to do is find derivatives of this thing. And I think I pointed out before, it's usually better if you don't simplify these things, right? So next one I've got negative 1 times negative 2 times 2x minus 7 to the negative 3, and I'm going to multiply it by 2 again for chain rule. Third derivative, I've got negative 1, negative 2, negative 3, 2x minus 7 to the negative 4, 2 to the 3. Now we were looking for the third order Taylor polynomials. That's all we need for part A. Okay, so for part A, now I'm centering this thing at x equal to 3, so f of 3 is what? 6 minus 7 to the negative 1, so it's just negative 1. F prime of 3 is negative 1 times negative 1 to the negative 2 times 2, that's negative 2. F double prime of 3 is, let's see, negative 1 times negative 2 times negative 1 to the negative 3 times 4. So what have I got? Negative 8, is that right? Because the negatives all cancel except for this one. So it's negative 8. Alright, and one more. F triple prime of 3. It looks like out front I've got a negative 6. And then I've got negative 1 to the negative 4. And then I've got 8. So this is what, negative 48? Okay, so there's my first three coefficients. So P3 of x should be f of 3 plus f prime of 3 times x minus 3 plus f double prime of 3 times x minus 3 squared over 2 factorial. And then same thing with the third power and the 3/4, all right? Okay, so it should be negative 1 minus 2 times x minus 3 minus 8 over 2 factorial is what? 4 times x minus 3 squared minus 48 over 6 is 8 times x minus 3 cubed. So that should be what we're looking at for the Taylor polynomial centered at 3. Okay. So third order Taylor polynomial. And even if you didn't simplify it, I think it's okay. So if you put dot, 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 you probably got dot to half a point for this. That's reasonable because the third degree Taylor polynomial doesn't keep going. It stops right here, right? So that's P3. In order to get the actual Taylor series, we need to come down and figure out what the nth derivative looks like. So first of all, let's collect our pieces here. How many negatives do I have? looks like n of them, right? Third derivative's got 3, second derivative's got 2, and so on. I've got 2x minus 7 to the negative, looks like n plus 1, right? Because when I take a third derivative, I have 4. Second derivative, I have 3. How about powers of 2?
And
Yeah, it's just n. Okay. And so in particular, the nth derivative at 3, well, I've got negative 1 to the n. I've got 6 minus 7 to the negative n plus 1. And I've got a 2 to the n. Oh, and there's an n factorial somewhere.
What happened to the n factorial?
Yeah, n factorial comes from 1 times 2 times 3 and so on, yeah. Okay, so,
You said the over n factorial?
well, the n factorial comes from these
Oh,
numbers
yeah.
building up. I'm gonna divide it by n factorial in a minute. So, the b, let's see what I gotta do. Definition of the Taylor series. I know the coefficient of x minus 3 to the n is nth derivative at 3 divided by n factorial, which is, now what's happening with my negatives here? This is 6 minus 7, which is negative 1. So I've got n powers of negative 1 on top and n plus 1 of them on the bottom. So I should have 1 left over, right? And that makes sense with what I'm seeing with my Taylor polynomial. All my coefficients are negative. So I've got a negative out front, and I've got, it looks like a 2 to the n times an n factorial on top, and then I'm dividing by n factorial. So it looks like it's just the negative of 2 to the n. Okay. So this is negative 2 to the n. All right. So that means the series f of x looks like k equals 0, or I guess I can do n equals 0 to infinity. Now I'm supposed to have the nth derivative at 3 divided by n factorial, which is the negative of 2 to the n. Alright, and that's times x to the n. Oh, it's not x to the n, it's x minus 3 to the n. So I think that's it. Yeah, okay. Any questions about this one? Okay. And I think this is your page. Alright. So that's a test. Enough of that and on to more fun stuff. Got a box of small, dangerous looking toys. We'll take one of those and pass them around. It's gonna be a fun day.
I want to be an observer. Spectator.
You are a spectator. Well, better than a spectator, you're a participant. So, we need to start talking about solids of revolution. Alright, so this is kind of the next step that we're doing. We've been determining volumes of things by slicing them into parts, right? Into thin slices. Alright, so the idea behind a solid of revolution is take a graph that you know, some kind of a graph, doesn't matter what it is. Now if I wanted to find the area below that graph, what would I do? I would slice it up into little tiny rectangles, right? And I would calculate the area of each one of those rectangles. And we were doing some of that on Monday. So what I'm interested in is revolve this guy around the x-axis till I get a solid object. And so the question is, well, what kind of thing is that? regular graph, right? And so what are we doing? This dial in the middle is our x-axis. And I'm rotating it around, and you see the solid object being formed here. It's like a vase, right? Some people say it looks like a vase. Some people say it looks like a wine glass, depending on which way you have the bottom, right? So the idea is, if I go around this thing, what I get is a shape made out of circular cross sections. Kind of looks like that, right? And the question is, how do I find the volume of that guy? Well, what happens to this blue segment here? What does that turn into when I spin it? It turns into a disc, right? So the whole point is, when I spin this section around the x-axis, what I'm going to get is just a disc, right? And so I should be able to find the volume of one of these objects by adding up the volumes of discs. So now if our tiny rectangles, tiny rectangles are usually long, skinny rectangles, right? If those are perpendicular to the axis of rotation, shapes of the cross sections are circular discs. All right, so okay, so how would you find the volume of one of those? Yeah, it's an area of a circle times a like a thickness, right? So it's going to look like a pi times a radius squared times a thickness. Now these things are very thin, so I figure my thickness is just going to be my dx term, right? Okay. What's the radius of this guy? Like for the disk right here,
X, Y.
it's the y coordinate on the graph, right? So it's a function value. So in this case, it's going to be f of x. All right. So you can say, well, disk method, my volume is going to be the integral from a to b of pi times f of x squared dx. Now, a couple of ways to look at this. Now, I know some people have just gone through, when we cover this stuff, there's various ways that you can build solids out of shapes like this. You can memorize about 8 different formulas, or you can get used to the idea of what's inside the integral is the volume of one tiny slice of what we're doing, right? And so that when we integrate it, we get the total volume. So the way to reconstruct this formula is always to get the volume of one whole slice of what you're working with. All right, so, and that's kind of the punchline of this whole section. We're going to be doing that with a lot of different volumes and other physical quantities. All right, so we've got this guy. Let's try it for a particular function. Suppose we revolve f of x equals, let's say, x squared plus 1 around the x-axis for x between -1 and 1. All right, so let's see if we can figure out what this thing looks like. Now y equals x squared plus 1 is this kind of a shape. All right, now I'm revolving around the x-axis. The way I do it is kind of draw an upside-down version of it down here, and then these things are connected with circles. So is there a thing that looks like that? Ooh, you ever seen those wicker chairs, right? This is like a nuclear power plant tower laying on its side, right? It's this kind of thing. Yeah, that's the shape that we're looking at. So, all right, we're going to break it into discs. So the volume is going to be the integral from -1 to 1. Well, let's say I've got pi times the radius squared times dx. And in this case, do you see where the radius of this particular circle is just going to be x squared plus 1? So it's going to be pi times x squared plus 1 squared dx. All right. So what we're going to run into in this section is you're going to see why we needed all those integration techniques at the beginning of the course. Because they're going to come up in these applications. When I teach this as an independent section that's not coordinated with a whole bunch of them, I like to interlace this stuff in with the integration techniques so you can see why you need the techniques that we cover. They order it this way in this class, so we do the easy stuff at the end, so that if you end up dropping, you've seen all the hardest stuff, so you can take it again. All right, so anyway, how do you integrate this guy? Probably just multiply it out. This is x to the 4th plus 2x squared plus 1, -1 to 1. All right, so this is pi times, it'll be 1/5 x to the 5th plus 2/3 x cubed plus x. All right, so it'll be 1/5 plus 2/3 plus 1 minus -1/5 minus 2/3 minus 1. So do they cancel or add up? They better add up, right? Because the volume's not 0.
Yes.
So that wouldn't be good, right? All right, so this is pi times 2/5 plus 4/3 plus 2, right? And I guess let's do the third grade arithmetic problem. Common denominator is 15. 2/5 is 6 out of 15. 4/3 is
20.
20 out of 15. And then 2 is 30 out of 15. So 26, so 56 over 15. So 56 pi over 15. And that's the volume of this thing. Okay. Now, that's it.
It's an easy cheesy.
Woo! Yeah. So, all right. Well, what else could we do with these things? Suppose instead that we revolve our graph around the y-axis. All right, so let's go back to this graph for now. All right, let's say the y-axis is over here. So this whole thing's on the first quadrant. So here's what my function is. Now, if I wrap this thing around the y-axis, what I'm going to get is another copy of it over here, right? And if I take the region below that and revolve it around the y-axis, I'm going to get something with circles that come out this way, right?
Mm-hmm.
So what shape is that? Like a brake drum, or maybe like a cake, right? Doesn't it look kind of like a brake drum, right? Or like a bunt cake, maybe? So, right, because it's going to have a hole in the middle of it, but it's going to come down here on both sides. Yeah, so that's what we're going to look like. Okay, and the question is, what kind of a shape do we get if I take this guy and I rotate it around an axis that it's parallel to? And by the way, are you seeing the point of the toys now? My hope was that you would be completely unable to stop from twiddling them, and you can see the kind of shape that you get, right? So somebody's got a shape that looks like this, right? If you got one of the ones that looks like this, what kind of shape are you looking at when you spin it?
Cylinder.
It's kind of like a little short section of pipe, right? So what you get when you spin this is you get another copy over here, and it's connected by circles. It's like you got a thin shell of a pipe, right? So we're going to call this a cylindrical shell. When we revolve a skinny rectangle around a parallel axis, right, like this, we get a cylindrical shell. You get a shape that looks like this. Okay, and we got to figure out a way to approximate the volume of this thing. So,
Can we take this into the test with us?
Oh yeah, that's right.
I think it might be distracting to the other people taking the test.
Or if
Yeah.
everybody has
If you've
one.
ever had like a pin clicking guy next to you,
I
yeah.
don't recall having
One of my students was about to psycho out last year at the community college. Yeah, so it's the guy next to him was, and I could see him kind of like the Incredible Hulking next to him. Yeah, so like it wasn't gonna end well. All right, so the thing is, we've got a shape. Looks like this, right? It's a cylindrical shell. So it's very thin. How am I going to determine the volume of this thing? What I'm going to do is this thing, right? I'm going to unroll it, right? So if I unroll this particular shell, let's say I cut it right here and unroll it, I'm going to get like unroll it like you would unroll that pipe insulation, right? You know what I'm talking about, the foam stuff that you put around the pipes? So you unroll it and you got like a flat pad of foam. Okay, so how big is this thing? Yeah, we got base times height. Now, do you see where this is basically a circumference of a circle? Right, so that's going to look like 2 pi times the radius. Okay, and then I've also got a height. Now let's see what I'm looking at here. If I'm going around the y-axis, do you see where the radius is actually just my x-coordinate? Right? So here, radius is just x. Okay. And what about the height of this thing? Yeah, you see where it's your y-coordinate? So it's just going to be f of x. This marker writes great, so much fume. So it's
We can smell it from the front row.
smell
you can smell it up
Yeah.
there, right? Yeah.
Yeah.
The good news is it writes forever. The bad news, it was banned by the FDA. So
You're letting brain cells right now.
what's it?
He says kill brain cells.
It's killing your brain cells.
We
right
got
now.
a million of them.
Yeah, who knows what I would have amounted to, right?
Exactly.
Yeah. All right. So what you see in your shell method is your volume looks like the integral of 2 pi times the radius times the height. And again, once you know what these measurements are, you just have to fill them in, and then you got what you're integrating. So, oh, do you see where the thickness is going to be your dx? So what we're actually calculating a small volume, right? Because it's the width of that tiny rectangle there. All right. Alright, so for example, suppose I revolve the region below y equals x squared plus 1, where x is between -1 and 1, around the y-axis. And again, let's find the volume. All right. Okay, so first of all, what kind of shape is this? It's kind of like a bowl, right? So it's, you can think of it as like, it's gonna be like a cylinder on the outside, right? Because I'm going all the way from here to here, I'm looking at the region below it, but it's got kind of like a bowl carved into it. So it's like a prehistoric drinking cup, right? That's what we're looking at this time. All right, so if we're gonna break this down into cylindrical shells, all right, so the volume is gonna be the integral of the volume of one shell, which is going to be the integral of, now I need 2 pi times the radius times the height, and I'm going to have a dx. Alright, what do you want for your limits of integration here? Okay. So what I've got is the integral from -1 to 1 of 2 pi, what's my radius?
Radius.
Well, it's the distance from the axis to the rectangle, right?
X.
Do you see where it's just your x coordinate? Okay. So I've got x, and then my height is what?
X.
It's going to be f of x, right? Which was x squared plus 1. So I've got 2 pi times the radius times the height, dx. And again, it's fairly easy integral. Now this is 2 pi times the integral of x cubed plus x from -1 to 1. Alright, so this is 2 pi times, I've got 1/4 x to the 4th plus 1/2 x squared, evaluated at -1 and 1. Something crazy's happening. I've got 1/4 plus 1/2, and when I evaluate it at -1, I get 1/4 plus 1/2. What happened?
Cancel each side, cancel it out.
Yeah, okay, so the problem is, this drum is the same as this drum, right?
No.
So what I ended up with is, for every shell that I got here, I counted like an anti-shell over here, right? So whenever when your region is overlapping itself, you need to cut out the redundant part, right? So I really need to integrate from 0 to 1, right? Because that's where my,
And then multiply by 2?
don't have to multiply by 2, right? Because where does this shell go? The shell that goes through